Welcome to Chibuzor Mathphysics. In today's video, we are going to be dealing with the interpolation error. What exactly is the interpolation error? The interpolation error is said to be proportional to the distance between the data points to the power n, and therefore we can say that the interpolant is a polynomial and thus infinitely differentiable. So we are going to be differentiating that function up to the third derivatives in order for us to find the interpolating error. So we see that polynomial interpolation overcomes most of the problems of linear interpolation. When we consider any other approximate method that we use in interpolation, or like bisection method, Newton interpolations, and even series, the utility of polynomial interpolation cannot be stretched too far. So in this video, we are going to quantify the errors that can occur in polynomial interpolation, and we are going to develop techniques to minimize such errors using the theorem that we are going to use in order to determine the error in polynomial. So the definition of this interpolation error, the error is given by this formula. Error E represents the error with this subscript n, as I said earlier, of these two functions x and f to the power of n plus 1 by epsilon, multiply this by x, divide this by n plus 1 factorial. Of course, we can have x minus x naught, x minus x1, x minus x2 up to x minus xn. So you need to pay attention to this, that if the interval of a and b is not given, it therefore means that we take a b to be x naught and n. So we need the function in order to be able to compute an error bound. So at the end of this video, you should be able to know how to compute an error bound and how to find the interpolating error of any polynomial. Do well to subscribe to this channel as I take you through the error of interpolation. I remain your friend, Augustine Galagash. So now let us take the first example and see how we can find the error bound in this polynomial. So in this first example, we are given for the function cos x. The function is given by cos x, that is f of x is equals to cos x, where if you note in this example, we have the interval of a and b is given. So the interval x naught is equals to 0, x1 is 0.2 and x2 is 0.9. So we are to construct the interpolation polynomial of degree at 2 to approximate of this function 0.45. Then we find the actual error at 0.45, then use the theorem 3.3 to find the error bound for this error. So things to pay attention to: so kindly we need to pay attention to these values that we are given, the value of x naught, the value of x1 and the value of x2. Of course, we are going to construct the interpolation polynomial of degree at most 2 to the approximate of this function 0.45, and we are to find the actual error at 0.5 and use the theorem to find the error bound. So let us go through this and see what we are supposed to do. So using the Lagrange's interpolation method, we simply need to use the formula. For the purpose of how we derive this formula, you can watch my previous video on how to derive the formula for Lagrange's interpolation. So what we have done here in Lagrange's, we have x naught, which it can be represented by L. This can be given by x naught is equals to x minus this is x1 minus x2. Just a minute. So using Lagrange's interpolation method, we apply x naught into x minus x1. We have x minus x2. We have x minus x3. That is if we have up to 3 terms. Divide this by x naught minus x1, x naught minus x2, x naught minus x3. Of course, we multiply this by y naught. Plus we have now x minus x naught, x minus x2, because now we are operating on 1, so 1 will not be among x minus x3. We skip x1, so x1 minus x naught, x1 minus we have x1 minus x2. So this is what we have. X1, this is x1 minus x2 and x1 minus x3. Multiply this by y1. So this is exactly what we have done here. Our x naught was given. If you check, we have x naught to be 0, x1 is 0.6, and x so let's have that now. X naught is 0, x1 is 0.6, so x naught is equals to 0, x1 is 0.6, and x2 is given as 0.9. So we substitute this in the formula. We have x minus x naught, which is x1, which is x1 is 0.6, into x minus x2, which is 0.9. Divide this by 0. Because 0 is our x naught and this is the x naught value, so we substitute this. When we do this, our value for x will simply be this. So this is what we got. Now our main target is to find the error bound. So px here represents the polynomial, interpolating polynomial. So the interpolating polynomial will be equals to x naught plus cosine of 0.6, because we are to evaluate according to this given function. We are to evaluate, if we go back to the equation that we are given, find the actual error at 0.45. The actual error at 0.45. So it is 0.6, which is our x1, and 0.9, which is our x2. So it is cos 0.6 for x1 plus cos 0.9 for x2. And if you observe this graph shows us the interpolating polynomial of this function f of x. And now the solution to this will be to find the interpolating polynomial of at 0.45 as we were given, because we were given 0.45. It will be, plug this in your calculator, but make sure that your calculator is in radians, so that you will have 0.89 0.81074. For cos 0.45, this is what you will get for cos 0.45 when your calculator is in radians. So to find the actual error at x equals to 0.45, it is simply 0.45 minus the interpolating polynomial of this function 0.45, so that the approximate error will be 0.0023. 0.0023. But to find the error bound, remember in the introduction I told you that it is differentiable. So it means that we are going to differentiate this function 3 times. The third derivative of this will give us the error in this approximation. So from here, if we observe from the previous graph, we can note that the maximum error is less than equal to 0.4. As indicated in this graph, it is less than equal to 0.4 because you can see this graph is donated the error to be at 0.6. Therefore, we can see from the figure that I already shown you that the maximum error in this function is less than equal to 0.4. However, we will not be able to compute this best bound because we don't know the location of epsilon, because we don't know whether it is increasing or it is decreasing. So for us to do that, we will bound the error into step 1. We need to find the maximum error, that is a is less than equal to x and it is less than equal to b. And to do this, we need to find the third derivative of x before we are able to compute and use the maximum error of this x and find the error bound. So to do this, we simply need to differentiate cos x, and the function is given by cos x. If we differentiate cos x, we get negative sine x. The second derivative will give us negative cos x, and the third one will simply be sine x. And if you observe, you note that sine x is increasing over with 0, 0, and 9. Hence, we can say that the maximum error or the error bound in this polynomial will be given by sine x, which is less than equal to sine 0.9. And this is how we calculate error bound. So our final solution would be x into x minus 0.9, because this is what we got here. If you remember when we are using the Lagrange's interpolation method, so simply plug it here right now so that we have this, and the g of x becomes x into x minus 0.9 and multiply into x into minus 0.9. The g prime of x will be given by 3 into x squared. If you open this together, minus x plus 0.18, and this becomes equal to 0. Therefore, our integrating polar in this function will be given by p1, which is 0.23 up to that, and p2. And this is exactly the solution to this question. So if you put together the two estimates of the first error and the error bound, you will have 0.057046, which gives us 0.007446. Hope you have enjoyed this video. In the next video, we will be taking more other questions on how we can construct the Lagrange's interpolation polynomial of degree 2, but this time around we shall be dealing with sine ln natural log of x. See you in our next video. God bless you.